Galvanic cells, which are also called voltaic cells, use a thermodynamically favorable reaction to generate an electric current. Before we look at a diagram of a galvanic or voltaic cell, let's first look at the half reactions that are going to be used in the cell. In the first half reaction, zinc metal loses 2 electrons to turn into the zinc 2 plus cation. Loss of electrons is oxidation. Therefore, this is the oxidation half reaction. As a quick review, the other way to tell that this is the oxidation half reaction is we go from an oxidation number for solid zinc of 0 to an oxidation number for zinc 2 plus of +2. An increase in the oxidation number is oxidation. Therefore, zinc metal is oxidized. And here is the other half reaction that we're going to see in our galvanic cell diagram. In this half reaction, the copper 2 plus cation gains 2 electrons to turn into solid copper. Gain of electrons is reduction. Therefore, this is the reduction half reaction. The other way to tell that this is the reduction half reaction is to look at the oxidation numbers. So the copper 2 plus cation has an oxidation number of +2, and solid copper has an oxidation number of 0. Since there's a decrease or a reduction in the oxidation number from +2 to 0, this is the reduction half reaction. A good way to remember which half reaction is which is to think about Leo the lion goes grrr. So loss of electrons is oxidation, and gain of electrons is reduction. When we add the two half reactions together, we have 2 electrons on the reactant side and 2 electrons on the product side, so those cancel out, and that gives us solid zinc plus copper 2 plus ions goes to zinc 2 plus cations and solid copper. In this redox reaction, zinc metal is oxidized to zinc 2 plus cations, and copper 2 plus cations are reduced to solid copper. Delta G naught for this reaction at 25 degrees Celsius or room temperature is less than 0, which means this reaction is thermodynamically favorable. Therefore, if we were to put a piece of solid zinc in an aqueous solution of copper 2 plus ions, we would see copper metal form on the zinc metal, and zinc 2 plus ions would form in solution. So that's what would happen if we did this reaction in only a single compartment. However, in a galvanic or voltaic cell, each half reaction gets its own compartment, and the 2 compartments are connected with a wire. Therefore, a thermodynamically favorable redox reaction is used to generate an electric current in the wire. And by electric current, we're talking about the flow of electrons. Now that we've gone over the half reactions in detail for this zinc-copper galvanic or voltaic cell, let's look at a diagram of this cell and see how things actually work. Let's start by looking at the compartment on the left, which is a beaker that contains a 1 molar aqueous solution of zinc sulfate. Therefore, there are zinc 2 plus ions and sulfate anions in aqueous solution in the beaker. We saw from the oxidation half reaction that solid zinc is oxidized and turns into zinc 2 plus cations. When zinc turns into zinc 2 plus, 2 electrons are lost. So those electrons will move in this wire that connects the 2 compartments. So imagine we have movement of electrons going from the compartment on the left towards the compartment on the right. This piece of solid zinc is called an electrode. The electrode at which oxidation takes place is called the anode. So let me go ahead and write anode in here. Next, let's look at the compartment on the right, which is a beaker that contains a 1 molar solution of copper sulfate. So in this beaker, there are copper 2 plus ions and sulfate anions in aqueous solution. We know that electrons are moving in this wire that connects the 2 compartments. And at the surface of this copper electrode, the copper 2 plus ions come in contact with 2 electrons and are reduced to form solid copper. The electrode where reduction takes place is called the cathode. So the copper electrode is the cathode for this cell. I went ahead and rewrote each half reaction to remind us of what's going on in each compartment so we can think about what's going to happen to our cell over time. The anode is where oxidation takes place, so solid zinc turns into zinc 2 plus cations. So as time goes on, the amount of the solid zinc electrode will decrease, and the amount of zinc 2 plus cations in solution will increase. And the cathode is where reduction takes place. So as copper 2 plus cations gain 2 electrons to turn into solid copper, over time the amount of solid copper electrode will increase, and the concentration of copper 2 plus ions in solution will decrease. A good way to remember that oxidation occurs at the anode and reduction occurs at the cathode is to think about two animals, an ox and a cat. So thinking about an ox reminds us that oxidation occurs at the anode, and thinking about a red cat reminds us that reduction occurs at the cathode. The next part of the cell that we have to think about is the salt bridge that connects these two compartments. Inside the salt bridge, there's an electrolyte solution such as sodium nitrate. The electrolyte is often in a gel or paste form to prevent early mixing with the other compartments. The solutions in each compartment, also called a half cell, must remain electrically neutral, and the purpose of the salt bridge is to balance the charges. Let's start by thinking about the compartment or the half cell on the left. When we started, we had equal concentrations of zinc 2 plus and sulfate anion, so the charges were balanced. However, over time, the concentration of zinc 2 plus ions increases. To balance out the increased positive charge, the negatively charged anion, in this case the nitrate anion, moves from the salt bridge into the half cell on the left. Next, let's think about the compartment or the half cell on the right. We started off with equal concentrations of copper 2 plus cation and sulfate anion. However, over time, there's a decrease in copper 2 plus cation. Therefore, there's too much negative charge in this half cell. To balance out the negatively charged sulfate anions, the positively charged ion in the salt bridge, in this case the sodium cation, moves from the salt bridge into the half cell on the right. A good way to remember which direction the ions go in the salt bridge is to think about anions going toward the anode and cations going toward the cathode. The salt bridge is necessary for the galvanic cell to work. If the salt bridge were removed, the electrons would stop moving in the wire. And that brings us to the last component of our galvanic cell, which is this voltmeter here. For this particular galvanic cell, with 1 molar concentration of zinc sulfate, 1 molar concentration of copper sulfate at 25 degrees Celsius, the initial voltage would be 1.10 volts. So that's what would show up on the voltmeter. The voltmeter measures the difference in electric potential between 2 points, and as long as there's a difference in electric potential, electrons will flow in the wire. However, this thermodynamically favorable redox reaction doesn't last forever. Eventually, the reaction reaches equilibrium, and at that point, the voltage is equal to 0. And when the voltage goes to 0, the current also goes to 0, which means the electrons are no longer moving in the wire. You could also call a galvanic or voltaic cell a battery, so at that point, the battery is dead. Let's do a quick summary of galvanic or voltaic cells. These cells use a thermodynamically favored redox reaction. This redox reaction generates an electric current that flows in the wire between the two electrodes. The electrode where oxidation takes place is called the anode, and the electrode where reduction takes place is called the cathode. A salt bridge is used to balance the charges in the two compartments. Eventually, the reaction reaches equilibrium, and at equilibrium, the voltage is equal to 0, which means there's no more current, and the galvanic or voltaic cell stops working.